So we are going to finish off chapter 2 today with the logic of compound statements and the application of that sort of thing with number systems and circuits for addition. So binary representation of numbers. Any integer greater than 1 can serve as a base for a number system. In computers, base 2 notation or binary notation is of special importance because of the signals used in modern electronics are always in one of only 2 states, which is not technically true, but we'll go with it for these purposes. There's actually 3 states, but you can only read 2 of them. So base 2 is used in computers. Derive the binary notation for the integers from 1 to 9. You notice the first digit on the right is the value of the symbol 1 times 2 to the 0th power. Let's see here. We'll do this. Come on. Right, of course. This thing doesn't like me. Okay, let's go back to where we were. So the first number 1 is 1 times 2 to the 0th power. Because you only have 2 symbols for binary notation, you get to 1, you have to roll over to 0 and add 1 to the next column. The next column has the value of 2 to the 1st power, or 2. So that's your 2's position. So 1 plus 0 in the 1's position is 1, 0 for 2. 1, 1 for 3. Again, rolling over, adding 1, you get you roll over from 1 to 0. Add 1 to the next column, which is also rolled over to 0, and then another 1 into the 4's column, or 2 to the 2nd power. So your numbers are 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, and then 9 is 1, 0, 0, 1, which is 1 in the 8's position, 0 in the 4's position, 0 in the 2's position, and 1 in the 1's position to make 9. The list of the powers of 2 is useful to know because that's the value of each position in a binary number. You start with 2 to the 0th power, or the 1's position, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, and so on up the line. So you can convert by multiplying the value of the symbol in each position by its corresponding decimal value for that position, and get and add them up together to get the decimal value. So 110101 would be a 1 in the, what is it, 2 to the 5th power position, which is 32. A 16, which is 48, right? No 8th position, a 4 position, a 1 in the 4th position, so you add 4, do be 52. 0 in the 2's position, and 1 in the 1's position, so it would be, total would be 53. And that's what they do here. You can also do this type of arrangement to get the same answer. Represent 209 in base 10 in binary notation. Well, 2 to the 7th, yeah. And then you subtract subtract 128 from 209, which is 81. 81 is between 64 and 128, so then the highest power of 2 that is less than 81 is 64. So you add 64. Then subtract that from 81, which is, what is that, 17, and then 16, and then 1. And so you put those 1s in the appropriate positions, and which yields 1101 0001. So binary addition and subtraction. Now, the computational methods for binary arithmetic are analogous to those of decimal arithmetic. In binary arithmetic, the number 2, which equals 10 in binary notation, plays a similar role to that of the number 10 in decimal arithmetic. So, add these two numbers together. To do that, you add 1 and 1 equals 10. Argue that with your elementary math teacher. But it follows that adding two 1s together results in a carry of a 1 when binary notation is used. Adding 3 1s together also results in a carry of 1, since 3 is 1 1. 1 1 base 2. So 1 plus 1 plus 1 equals 11, or 1 1. Thus, the addition can be performed as follows. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 1 is 0, carry the 1. There's your answer. Now subtract. I'm going to skip over this one because this is not. I'm going to skip over subtraction because that's not the way computers do subtraction. They do the borrowing method and all that sort of stuff, which is the same as decimal. You'd borrow 1 from the if the top number is less than the bottom number, you borrow 1 from the next column over and do the subtraction that way. It's kind of tedious and annoying, but you can do it that way in binary as well. Just you're borrowing 2 instead of 10. So circuits for addition. How a subtraction is done in computers is the addition of a negative number. You convert the number into a negative number and then add them together. So that's how computers do subtraction. Circuits for computer addition. So you have your state table of what inputs you have and what outputs you're going to have. The circuit for addition has 2 inputs for your A and B, or P and Q here. Both P and Q can be either 0 or 1. The outputs have 2 columns, therefore it must have 2 outputs. The first column on the right is the sum, and the carry is the second column. The carry output is 1 if both P and Q are 1, it is 0 otherwise. Thus the carry can be produced using the AND gate circuit, which corresponds to the Boolean expression P and Q. The sum output is 1 if either P or Q, but not both, is 1. The sum can therefore be produced using a circuit that corresponds to the Boolean expression for exclusive OR. So you have this circuit for a half adder. Why it's called a half adder we'll get to in just a minute. But P or Q and not P and Q for the sum, and P and Q for the carry. Okay? Why aren't you? Did you want to get a picture of that? Yeah. Okay. All right. All right. Now consider the question of how to construct a circuit to add 2 binary integers, each with more than 1 digit. Because the addition of 2 binary digits may result in a carry to the next column to the left, it may be necessary to add 3 binary digits at certain points. In the following example, the sum in the right column is the sum of 2 binary digits, and because of the carry, the sum in the left column is the sum of 3 binary digits. So, construct a circuit that will add multi-digit binary numbers. It is necessary to incorporate a circuit that will compute the sum of 3 binary digits. Such a circuit is called a full adder. It is constructed using 2 half adders. But the operation of the full adder is based on the fact that the addition is a binary operation. Only 2 numbers can be added at one time. Thus, P is first added to Q, and then the result is added to R in this example. So you have a half adder and 2 half adders and an OR for the carry. If the carry in either half adder is 1, then there's a carry out on the full adder output carry. And the input-output table or state table looks like this. Sum is 1, carry is 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, or 0. The use of blocks and stuff like that too, and similar shortcuts is common, so you don't have to draw out the full half adder circuit twice. It is assumed that that the reader knows what a half adder circuit looks like, so you just do the black box, so that sort of thing. Two full adders and one half adder can be used together to build a circuit that will add two 3-digit binary numbers, PQR and STU, and obtaining the sum WXYZ. You cascade the carries from the half adders and the full adders into the next columns. This produces what is known as a ripple adder, because the carries ripple down through the circuit until the final result is valid. Two's complement and the computer representation of signed integers. Two's complement is how you represent negative numbers. Typically, a fixed number of bits is used to represent integers on a computer. One way to do this is to select a particular bit, normally the leftmost, to indicate the sign of the integer, and to use the remaining bits for its absolute value in binary notation. The problem with this approach is the procedures for adding the resulting numbers are somewhat complicated, and the representation of 0 is not unique. A more common approach is to use 2's complements, which makes it possible to add integers quite easily and results in a unique representation for 0. Bits of 64 and sometimes 32 bits are most often used in practice, but for simplicity and because the principles are the same, we'll discuss it in the bit length of 8. So, 2's complement for an integer a between negative 128 and 127, positive 127, is the 8-bit binary representation for a, or the binary representation of 2 to the 8th minus a, the absolute value of a, if a is less than 0. But there's an easier way to do that. Convert your absolute value of your number into binary form. Do they do that? Oh yeah. Write the 8-bit binary representation of absolute value of a. Switch all the 1s to 0s and all the 0s to 1s, or flipping the bits, or complementing them, and then add 1 in the binary notation. That gives you the 2's complement value representation of the number. And also do the same process to get back to the decimal. If you have a 2's bit complement 2's complement binary number, you flip the bits, add 1, and then take the decimal value of that and then put a minus sign in front of it if it's a negative number. But use this method described above to find the 8-bit 2's complement for negative 46. Well, first you get the value for 46 in 8-bit form, so 46 only uses 6 bits, so you add 2 leading zeros to it to make it 8. Then you flip the bits, and then you add 1. So your 8-bit 2's complement representation of minus 46 is 11010010. The fact that this method works for finding 8-bit 2's complements works in general depends on the following facts. The binary representation of 2 to the 8th minus 1 is 8 ones. Subtracting an 8-bit binary number A from 8 ones switches all the ones to zeros and all the zeros to ones. Thus, 2 to the 8th minus the absolute value of A is equal to 2 to the 8th minus 1 minus the absolute value of A plus 1 for any number A. So it goes through the process of switching and subtracting and all that stuff. Because 127 is the largest integer represented in the 8-bit 2's complement system, because it's 0, 1, 1, 1, 1, 1, 1, 1, all the 8-bit 2's complements for non-negative integers have a leading bit of 0. Because the bits are switched, the leading bit for all negative integers is 1. This shows how it works in a number line, so to speak. Find the decimal representation of the negative integer with a given 8-bit 2's complement. Apply the 2's complement procedure to the given 2's complement and write the decimal equivalent of the result with the so it works both ways. What is the decimal representation for the integer with 2's complement? 10101001. Well, you flip the bits, add 1, and then because this is a leading 1, you have the resulting decimal number is going to be negative. So flip the bits, add 1, and then find the decimal representation of that number, which gives you minus 87. So there you go. Addition and subtraction with integers in 2's complement form. This is the easy part. The main advantage of a 2's complement representation for integers is that the same computer circuits used to add non-negative integers in binary notation can be used for both additions and subtractions of integers in a 2's complement system of numeration. First, note that because the algebraic identity a minus b equals a plus negative b for all real numbers, any subtraction problem can be changed into an addition one. For example, suppose you want to compute 78 minus 46. This equals 78 plus negative 46, and should give you the answer of 32. To see what happens when you add the numbers in their 2's complement forms, observe that the 8-bit 2's complement for 78 is the same as the ordinary binary representation of 78, which is that number there. And because and the 2's bit complement for 46 is 11010010. Now you add the numbers together, and you get 32, kinda. The result of it has a carry bit of 1 in the 9th position, but if you discard it, you obtain 32, which is the correct answer for the 8-bit 2's complement form, because since 32 is 2 to the 8th, right there. No, 32 is 2 to the 1, 2, 3, 4, 5, 5th power. 2 to the 5th power, not 2 to the 8th power. That's typo in the slides. I did not create these slides. General procedure for using 8-bit 2's complements to add two integers. Add two integers in the range of minus 128 through 127, whose sum is also in the range of minus 128 through 127. Convert both integers to their 8-bit 2's complement representations. Add the resulting integers using ordinary binary addition, discarding any carry bit of 1 that may occur in the 2 to the 8th position, and then convert the result back to decimal form. Now, hexadecimal notation. As was stated earlier, computers often use 64 or 32-bit representations of numbers internally. 64 bits is, well, 64 numbers. That's quite a bit. We use hexadecimal as a shorthand because it's more compact than decimal notation, and it's easier to convert back and forth between hexadecimal and binary. It is base 16, hex and decimal, hexadecimal. So hexadecimal notation is based on the fact that any integer can be uniquely expressed as the sum of numbers of the form d times 16 to the nth power, where each n is a non-negative integer and d is one of the integers from 0 to 15. Being base 16, there are 16 symbols used for a hexadecimal. These are their representations in decimal form, hexadecimal form, and binary equivalent. Hexadecimal goes from 0 to 9, and then A, B, C, D, E, F. And each combination, or each hexadecimal digit, corresponds to a unique 4-bit combination of binary digits. There's a 1-to-1 correspondence. So, convert 3CF to decimal notation. Well, 2 to the 3 times 16 to the 2 to the second power C, which is 12, times 16 to the first power, plus 15 times 16 to the 0th power. Add those together, and you get 975. But to convert to binary from hexadecimal, you just write each hexadecimal digit of the integer in 4-bit binary notation and concatenate the results. So B09F in binary would be 1011 for B, 000 for 0, 1001 for 9, and 1111 for F, which gives you the answer here. Simple substitution. Nothing complicated. No, don't need to do any math. Just know the corresponding 4-bit representation of each of the hexadecimal digits. If you're encountering a situation where you need to do those conversions, like on a test or quiz or homework, I would suggest writing out this table here to the side so you can easily see the correspondence. So it goes both ways. So to convert integers written in binary into hexadecimal, reverse the steps of the procedure. Commonly used computer representation of integer uses 32 bits, or if it's a long integer, 64. When these numbers are written in hexadecimal notation, only 8 or 16 in the case of 64-bit characters are used. So it is much more compact to write 8-bit digits instead of 32. So it's going to go through its example here. First group of binary digits in sets of 4, working from right to left, adding leading zeros if necessary. And then you convert each group of 4 binary digits into a hexadecimal digit. Then you concatenate the hexadecimal digits together. Now, this gets into memory dumps, which I haven't seen on anybody do on a computer in a long time. But the smallest addressable memory unit on most computers is 1 byte, 8 bits. In some debugging operations, a dump is made of the memory contents. That is, the contents of each memory location are displayed or printed out in order. To save space and make the output easier on the eye, the hexadecimal versions of the memory contents are given rather than the binary versions. What is the actual memory content of these 4 memory locations? Well, the binary representations, because the memory is in binary, not in hexadecimal. And I think that is it for chapter 2. All right, let's see what we can get started on in chapter 3. Chapter 3 is the logic of quantified statements. All right. Predicates and quantified statements. A predicate is a sentence that contains a finite number of variables and becomes a statement when specific values are substituted for the variables. So, a statement finite variables, finite number of variables. I'm sorry, and with specific values. For the variables. A predicate is just the sentence with the variables. So a predicate variables. And it becomes a statement when you assign specific values to the variables. The domain of a predicate variable is the set of all values that can be substituted in place of the variable. Domain. Set of possible values. Okay. So, finding the truth values of a predicate. Let's see here. Take P of X as the predicate. P of X is equal to X squared is greater than X. With a domain of domain all real numbers. Which of the following are true? P of 2, P of 1/2, P of minus 1/2. Which ones are true? Sure. Okay, that is true because 2 squared to 4 is greater than 2, so true. The third is also true because minus so negative 1/2 is in fact less than the square, which is 1/4, positive 1/4. But this one is false, because 1/2 is greater than the square, which is 1/4. Okay? Now you can define a truth set as the set of all elements of D that make P of X true when they are substituted for X. P of X is denoted as being the truth set is X is an element of D such that P of X is true. That's how you you can denote the truth set of a predicate. The set of all X that are elements of the domain that make P of X true. So, say Q of N is the predicate, N is a factor of 8. So say Q of N is N is a factor of 8. All right. The domain is Z. Or integers. All right. What would the truth set be? And there we go. And the negatives. Minus 8, minus 4, minus 2, minus 1, 1, 2, 4, and 8. Everybody agree with that? Because this domain is all integers, not just positive integers. So you have to take into account the negative factors as well. All right, let's see here. The universal quantifier. Which is, the symbol for that is an inverted A. You can make a predicate a statement by assigning values to all the variables. This was done in the previous example. Another way to use this, to do this, is using quantifiers. Quantifiers are words that refer to quantities such as some or all, and tell how many elements, for how many elements a given predicate is true. A is inverted A is the universal quantifier, and it is read as for all, for each, given any, and or for for every. Okay. So the sentence, every human being is mortal, human is mortal, can be expressed for all x element of humans, x is mortal. For all human beings, x is mortal. For all x that is an element of the human race, it is mortal. X is mortal. So definition. Let Q of x be a predicate and D the domain of x. A universal statement is a statement of the form A, inverted A of x is element of D, comma, Q of x. It is defined to be true if and only if Q of x is true for each individual x in D, for the entire domain. It is defined to be false if and only if Q of x is false for at least one x in D. So if there's one element of the domain, it's not true, then the universal quantifier is false. A value for x which Q of x is false is called a counterexample to the universal statement. So, consider A over x element of D x squared. How is this written? Okay, greater than or equal to x. Okay. Where D equals the 1, 2, 3, 4, 5. This statement is true, and the way to prove it is what we'll learn later on is called an exhaustive proof. That it's true is you calculate x and x squared and compare them for each element in D. Now, if D is an infinite set, an exhaustive method is not possible. At least not conventionally. Well, an exhaustive proof is not possible with an infinite domain. So if you have the if x is an element of the real numbers, you can show that this statement is false by using a counterexample. Counterexample would be any ideas on a counterexample? Any number between 0 and 1. 1/2. 1/2, yeah. Counterexample. One half. And so this is false. Well, kind of the next quantifier kind of leads into this. There exists a example that makes this false. So you would imagine that the next quantifier would be the existential quantifier. That is the inverted E. And that is, there exists. Or for some. That sort of thing. Example, there is a student in Math 140. So that would be, there exists a P, which is an element of P, such that P is in Math 140. And P is all people. So, definition. Let Q of X be a predicate and D the domain of X. An existential statement is a statement of the form inverted E of X is an element of D such that Q of X is true. All you need is one. So all you need is one to make the statement true. So consider the statement. There exists a number m that's the element, which is an element of positive integers, such that m squared equals m. So there exists an element, there exists an m, which is an element of positive integers, such that m squared equals m. Is that what I said? Yeah. This isn't for all, because obviously that's not true. But there exists one example that makes this statement true. If true, because m equals 1 satisfies the equation. Now, if you say E equals 3, 4, 5, 6, you would have to show that this statement is false exhaustively by showing that for all elements of E, m squared does not equal m. Yeah.
There exists M.
Yes.
M in the element.
M is an element of positive integers. Yeah, Z is integers, and then the plus up here makes it positive integers. We're doing on time. We're doing okay. All right. Now, it is important to be able to go between formal and informal language when dealing with mathematical problems. Like this. This is formally expressed. So informally, there is a positive integer such that that integer squared is equal to that integer. That would be informal. And going back and forth is an important skill to have, to be able to translate between formal and informal language. Let's say for any integer n, 2n is even. That's informal. How would you say that formally, given what we've covered so far today, this afternoon? So any integer n is an element of integers, right? 2n is even. No, that's hold on. It's a comma, not such that. So this is informal. This is formal. Formal representations are more likely to be able to be manipulated, more easily manipulated using mathematical functions and procedures. Let's see here. There exists at least one real number x such that x squared is less than or equal to 0. There exists a number n, element of R, such that n squared is less than or equal to 0. See how the formal also is a lot more brief. Mathematicians and computer scientists are notoriously lazy. They like their notation to be brief and kind of coded so that you have to understand their language to understand their work. But let's see here. Universal conditional statements. Conditional. Universal conditional statements. They take the form for all x if p of x, then q of x. All right, so for example, for all x, there's the element of R. If x is greater than 2, then x squared is greater than 4. How would you say that informally? In pretty close. I'd say for every real number greater than 2, the square is greater than 4. Now, to not use the variables so much, but equivalent forms of universal and existential statements. Let's see here. Equivalent forms. Take the two statements. For all real numbers x, x, if x is an integer, if x is an integer, x is rational. Okay? That's the universal conditional that we covered earlier, that form that we covered just now. But this can also be written as for, actually, let me go ahead and write that in formal for all x element of R if x is an element of Z, then x is an element of Q. That would be the formal way of expressing that, which makes it easier to see where this can be written as for all integers x, x is rational. So you have for all x element of Z, x is the element of Q. Basically, what this is showing is that the universal conditional form here can be represented in a more simplified form if you can show that the set that the x is coming from is a subset of the original set, the original domain. If the domain is a subset of the original domain, you can consolidate and write it in a more simplified form. The reverse is also true. You can expand it out if, because Z is a subset of R, you can write if X is an element of Z, then X is an element of Q. All right, let's see here. An example here. Let's see here. All squares are rectangles. All right. So for all S, the element of S, S is an element of R. Right? Yes. For all squares that are for all S that are elements of squares, S is a rectangle. Is an element of rectangles as well. So the universal conditional form of that, for all S is an element of polygons, if S is an element of squares, then S is an element of rectangles, of the set of rectangles. Is that making sense? Going back and forth between abbreviated form, more verbose form. You can also put ands in here, so there exists a number n that's such that prime n and even. There exists a number such that n is prime and n is even, which is true because of the number 2. There just exists one, so that's all that is required for it to be true. But you can mix and match different functionalities. You can make this a and symbol. Let's see here. We are about out of time. So, Thursday, there will be a test on chapters 1 and 2. We will pick up again with chapter 3 on next Tuesday. But yes, open note calculators are recommended for the test on Thursday. If you have your notes on a computer, please print them out before you get to class. See you all on Thursday.